All right, welcome to Math 310, Introduction to Math and Algebra. This is lecture 11. So we're going to do yeah, okay. This is okay. We're going to do more stuff on rings and hopefully a little bit more on RSA and encryption. If not, we'll get to that on Tuesday's class. So last time we introduced a new concept, ring. So whenever you see a new concept, you always want to ask, what have you seen that might be similar to this? And so we're trying to generalize properties of the integers, properties of the rationals, properties of the reals, properties of the complex. And so a ring is a set with two operations, addition and multiplication. So we do plus for the addition, times for the multiplication. And under addition, R is supposed to be an abelian group. So not only is it a group, but it's an abelian group. Things commute. Under multiplication, we do not have a group. We almost have a group. We do not require the elements to have inverses. And there's one element in particular that we should not be expecting to have an inverse. What element would that be? So what element do you definitely have concerns about having an inverse, a multiplicative inverse?
Zero.
Zero, right? We should not be able to find a multiplicative inverse for zero. But maybe everything other than zero has an inverse. We've seen situations where that's not true. Can anybody give me an example where we have multiplication, but some non-zero elements don't have inverses? Which, okay, good. Good. So, if I just look at the integers, 2 does not have an inverse. But we could extend the integers to the rationals. And if we look at the rationals, then everything that's not a zero, does have an inverse. So looking at just the integers, we see the integers is not rich enough, but we could extend it and we get the rationals. We have seen a set where we have multiplication defined, but not every element has an inverse. And that includes some elements that are not zero. Can anybody remember an example of a set where we have multiplication defined and some non-zero elements don't have inverses? This is one of our go-to sets. Clock multiplication, right? How many hours? 12, right? So give me an example of something on a clock with 12 hours that doesn't have an inverse under multiplication. The even numbers, right? In fact, anything that has a factor in common with 12 won't have an inverse. And we saw that if we restrict to the elements that are relatively prime to 12, then we do get a multiplicative group. So it could be the case that under multiplication, not only does the zero element fail to have a multiplicative inverse, but non-zero elements could also fail to have a multiplicative inverse. All right. We want there to be an identity element, one satisfying, under multiplication, if you multiply on the left or the right, it does nothing. We want the associative law to hold. Implicit in this is closure. If we multiply two things in R, they stay in R. But we do not require multiplicative inverses. We are adding something new. We are adding the distributive law. And we've seen in some calculations why the distributive law is useful. In almost everything you've looked at in life, the distributive law holds. It would kind of be scary for the distributive law not to hold, but we do require that explicitly. And then an optional nice feature would be the commutative law under multiplication. A times B is B times A. If that holds, then we say the ring is commutative. Can you give me an example of a ring that's not commutative? And this is from a class you've taken to get here. Matrices are. So if I'm asking for a ring, so matrices under multiplication and under addition. So if you're going to be that explicit, you can just say matrices and I'll be fine. But as soon as you start to say matrices under multiplication, then you've got to say the other one as well.
I thought I said group.
Right. Oh, sorry. I might have. Okay. If I said group, then I'm wrong, because it's not a group, right?
Oh yeah.
So if I said group, and unfortunately, because this is being recorded for quality control, we can actually check afterwards and see, did I really say group or did I say ring? But yeah, so if you look at the matrices, 2x2 matrices, it's a ring, but it's not going to be a commutative ring. Okay. So one of the biggest questions you want to ask is, what properties from integers, or maybe from the reals, continue to hold as you go up to rings? So this is one of the general themes of the course. You start off with something nice, you build intuition from it, and then you try to see, does that hold in larger structures? So one of the most useful properties integers have is unique factorization. So if n is a positive integer, there exists a unique representation. Have people seen this notation before? The E and the exclamation point? Excellent. The unique representation, n equals p1 to the r1 dot 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 pk to the rk, where the pi's are prime, and p1 less than p2 less than dot 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 less than pk. I'm going to write the primes in increasing order so that I have a unique factorization. I really don't want to consider 2 times 2 times 3 to be different than 3 times 2 times 2. This is a wonderful property. And so you could ask, does something like this hold in general? And so in order to investigate something like this, we need examples of rings. So right now we have maybe clock under addition and multiplication. We have matrices. I'm going to give you another one. So example of a ring. Let X be a non-rational complex number. Consider the set S equals A plus BX. A and B are integers. Is this a ring? If not, for what X is it a ring? So maybe if I choose an arbitrary X, it's too much to hope that this is a ring. But if I put some additional properties on X, maybe it can be a ring. So can somebody give me an X to try? 1. Unfortunately, that doesn't satisfy my constraints on X. It has to be a non-rational complex number. So if I took X to be 1, then you would have all numbers of the form A plus B times 1. What would all numbers of the form A plus B times 1 be? Nope. Where do A and B live? A and B are, what does Z mean? Integers. So you have all numbers of the form A plus B times 1. So what do you get out when you look at all numbers of the form A plus B times 1? What do you get back? Integers. So if you take X equals 1, S is just going to be the integers. If you took X to be irrational, then you would basically just be getting all rationals with the same denominator as X. And if your X is 1/5, I would count 3 as having the same denominator by writing 3 as 15/3. Oh, I'm sorry, I said fifth, sorry, 15/5. So if X is rational, this is going to essentially reduce to integers plus fractions with the same denominator. So I need X to be a non-rational number. So can somebody give me a non-rational to try? Yes. Pi. I was wondering if people were going to do pi. So let's consider S to be the set of all a plus b pi, a, b are in integers. I'm going to change notation because I can. I'm going to call that S sub pi, and over here I'm going to call that S sub x. That way I can quickly determine what set I'm looking at. So we need to show that this is a ring, so we have to go through all the different properties. So addition. Do we have a zero element under addition? How would we get the zero element? How could we write zero in the form a plus b pi with a and b integers? You have to give me values of a and values of b such that a plus b pi equals 0. What could I do?
Set and b to 0.
Yes, a b is 0. 0 equals 0 plus 0 pi. Now let's do closure. If I have a plus b pi plus a tilde plus b tilde pi, that's a plus a tilde plus b tilde times pi. And this is an integer, and that's an integer. So I can go through and I can keep showing that all of the stuff holds. Okay. I'll leave the rest of addition for you. Multiplication. You think that this is almost a group under multiplication. Do we have an identity element? What do you think? Is there a choice of A and B that will give us 1? Okay, what would the choice be? 1 plus 0 pi. This isn't so bad. What else do we need to check? Do we need to check inverses? No. Do we need to check if it's commutative?
Yes.
We don't. It doesn't have to be commutative. It doesn't have to be commutative to be a ring. It's nice if it's commutative. What else do we have to check?
Closure.
Closure. Ah, you guys wouldn't remember closure. And then we would check associativity and see if associativity worked. And then we would get to closure. So if I give something in the form a plus b pi times c plus d pi, does this equal, say, e plus f pi? If it's closed, I have to show no matter what you choose for a, b, c, and d, I'm going to get something in the form e plus f pi. If I want to show it's not closed, I just have to find one example. Can somebody give me an example where it's not going to be closed? So can you give me an example of two numbers that I multiply and it's not going to be the form e plus f pi? So yes. Well, if b and d is 0, then you're going to just get a times c. That's fine, then what would f be? Right, so if you did a plus 0 pi times c plus 0 pi, that does equal e plus f pi with e equals ac and f equals 0. But that was a good thing to try, which says, let me take b and d to be 0 and make it really simple. So you were almost there. Instead of taking b and d to be 0, what should you do? Yeah, if you take a and c to be 0, you would get 0 plus pi times 0 plus pi is pi squared. Imagine that equals e plus f pi. then what can you deduce from this?
F must be pi, it's the rational number, or it's some integer.
I'm sorry?
F would have to be pi, and E would be 0. So
Right, so how do you know that? How do you know that there's no E and F that work? So you get pi squared minus F pi minus E equals 0. Therefore, pi equals F plus or minus the square root of F squared plus 4E all over 2. And what you would have now is pi is a quadratic irrational. So if this were going to be a ring, we need it to be closed under multiplication. And it would say there has to be some choice of F and E such that we can write pi like this. It's a deep question about what kind of number is pi. It's not too hard to show that pi is irrational. With a little bit of work, you can show, I'll call it easily, that pi is transcendental, that it's not the root of any polynomial of finite degree, by following a bunch of integrals line by line by line, where you have no idea why somebody is choosing to do these integrals, but at the end of the day, you get a contradiction. So once somebody has shown you the path, you can check each line very easily and see that if pi solved a polynomial of a finite degree, there's a problem. How many people have heard the word algebraic and transcendental? Okay. So an algebraic number is a number that solves a polynomial of finite degree. A transcendental number does not solve a polynomial of finite degree. So if this was closed, pi would have to solve a polynomial of degree 2. And so I can use the quadratic formula. I now need to use some advanced theory. I need to know that pi does not solve a polynomial of degree 2. So I'm not going to prove that. But once you have that, it turns out that S pi is not a ring. It's kind of a shame, because this is a nice set to look at, a plus b pi. I let a and b range over the integers. I choose some number pi that's not irrational. Okay, so we know that I can't just choose any x willy-nilly and have this be a ring. We saw that if we tried x equals pi, it wouldn't work. If you want a specific example, can you give me a number that you know is not a quadratic irrational? So pi is not a quadratic irrational. Can you give me a number that solves a polynomial of degree 3? What's the simplest equation you can think of degree 3? Okay, but then that gives you 0 as the triple root. So instead of x cubed equals 0, try x cubed equals
X cubed.
So give me a number. So if you tried 1, you would have 3 roots. One of them would be 1, and you would have 2 complex roots. Amazingly, in those cases, the 2 complex roots would be quadratic irrationals. I know everybody loves doing this. Let me see if I can do this. So if I give you x cubed equals 1, and that's the same as x cubed minus 1 equals 0, can somebody give me a root of x cubed minus 1 equals 0? A value of x that satisfies that equation? 1. So I can now factor this as x minus 1 times something. And we can do polynomial long division, which you might have traumatic memories from high school. There's also the method of divine inspiration. Have you seen the method of divine inspiration? And then so you stare up into space and then you just write down the answer. So let's multiply this out. So if I multiply this out, When x hits things, that's going to give me x cubed plus x squared plus 1. When the minus 1 hits things, that's going to give me a minus x squared, oops, this should be a plus x here. Minus x minus 1. And so when I add them together, I get x cubed minus 1. Using the method of divine inspiration, I have factored this and I don't have to use polynomial long division. So the roots are x equals 1 or x equals negative b, which would be negative 1, plus or minus the square root of b squared minus 4ac all over 2a, or negative 1 plus or minus the square root of minus 3 over 2. So unfortunately, when you gave me x cubed minus 1, it is a cubic equation, but the roots turn out to be quadratic. Maybe every irrational satisfies a quadratic equation with a little bit of work. No. So you have to give me another one. X cubed minus 1 didn't quite work. Try another one. X cubed equals. So x cubed minus 1 didn't quite work. What's something else we could try? Give me a number. Almost any number will work.
2.
2. So if we do that, then one root is going to be 2 to the 1/3 or the cube root of 2. And we can show that the cube root of 2 is not the same as the square root of something. It's not going to solve a polynomial of degree 2. So when we're looking at this, when we're trying to figure out what would be good x's to take, when we tried to look at pi, when we looked at closure, we saw that if we take a and c to be 0, we got pi squared had to be in the ring. And that forced pi to satisfy a polynomial of degree 2. So does anybody want to give me a good irrational pi? So study Sx equals a plus bx x, we'll do a and b are integers. What would be a good x to try that has a chance? So pi failed because we needed pi times pi or pi squared to be of the form e plus f pi. It had to satisfy a polynomial of degree 2. What would be a good x to try that we have a hope that maybe it could be a ring? Any thoughts? There's lots of numbers. What would be a good number to try? Do you think cube root of 2 would be a good number? Do you think cube root of 2 would satisfy its square is going to be solving a polynomial of degree 2? I'm looking for numbers that satisfy a polynomial of degree 2. Can you give me a number that satisfies a polynomial of degree 2? You know, cube root of 2 won't work. That satisfies a cubic, a degree 3 polynomial. What's a polynomial of degree 2? Give me polynomial of degree 2 that has roots you could calculate. Give me a number that satisfies a polynomial of degree 2.
Square root of 2.
Square root of 2. So let's take x to be the square root of n and not a square. So now, under addition, it's a ring. I'll leave that for you to check. We actually had no trouble when we took pi before, and we tried to see, was it a group under addition? That was no problem. So the ring properties hold here. Let's look into multiplication. Do we still have an identity element under multiplication? Can we write 1 in the form a plus bx? What do you think? Can we write 1 in the form a plus bx? Is this the same as what we had before? Yeah, it's just going to be 1 plus 0 times x. Associativity is free as these complex numbers. If complex numbers are associative, these will be associative. Do we have to worry about inverses? Do we have to worry about, no. So we just have to check what? What's the last property we have to check? Solution. So let's say I give you a plus bx times c plus dx. We multiply this out with 4, we'll get a times c plus b cx plus a dx plus b dx squared. But what does x squared equal? What did we assume? We assumed x equals the square root of n. So what would x squared equal? It would just be n. So we can group things, and so we'll get ac plus n plus bc plus a dx. It's closed. This is an integer. This is an integer. It's closed. So this tells us that if we want to look at rings, if we take things in the form a plus b square root of n, that will work. And so now the question is, what should I choose for my n? Any n that's an integer will work, as long as it's not a square. If it's a square, it still works, it just reduces to the integers. If I take n to be 4, the square root of 4 is 2, I just get all numbers in the form a plus 2b. Well, as a runs over all the integers, a plus 2b runs over all the integers. So I want to choose an n that's not a square. So there's an obvious natural choice. What's the obvious natural choice to try for n? First non-square that you can think of, it's 2. I don't want to do 2. I want to do -5. So I want to look at s -5, which would be all the numbers of the form a plus b times the square root of -5. Okay. And so if I give you some number z equals a plus b square root of -5, z bar would be a minus b square root of -5. And really, the square root of -5 is I times the square root of 5. Right? I'm just pulling out the -1. Okay. What's 2 times 3? This is basically who's awake right now. 6. Yep. Excellent. What's 1 plus the square root of -5 times 1 minus the square root of -5? Six. And in fact, that's why I wrote equals 6. We've just written 6 in 2 different ways. So what should be true about this number 2? What would you hope is true? Well, if you think back to integers, if a prime divides a product, it's got to divide one of the factors. So does 2 divide one of these? Let's try to see. Let's say we have 2 times a plus b square root of -5 equals 1 plus the square root of -5. So we would get 2a plus 2b square root of -5 equals 1 plus the square root of -5. Is there any choice of a and b such that this will work? Can we find any integers a and b where this will work? So I need to find a value of a such that 2a equals 1. Can you find a value of a such that 2a equals 1? Wait, no. So this is impossible. Similarly, if I tried to divide 1 minus the square root of -5, it wouldn't work. What if I tried the other way? What if I tried 1 plus, oops. What if I tried the other way? Maybe 1 plus the square root of -5 times a plus b square root of -5 equals 2. Is there some way to have this happen? Well, if I multiply things out, I'm going to get a minus b times 5 for the real part. And then I'm going to get plus a plus b square root of -5 equals 2. Because the square root of -5 times the square root of -5 is -5. So if this is going to be true, what's the only way this could be true? What must be true about a and b? Which one is easy to look at, the real part or the square root of -5 part? I think the square root of -5 part is easier. What does this have to equal? If we want this whole thing on the left to equal 2, what does a plus b have to equal? It has to equal 0. So a equals -b. So over here, if a equals -b or -b equals a, this becomes 5 times, I'm sorry, it becomes, let me do it slowly. A plus 5a, which is 6a, and that has to equal 2. Impossible. So we have a very strange situation. We have the number 6, and I can represent it as a product 2 different ways. One way is 2 times 3. Another way is 1 plus the square root of -5, 1 minus the square root of -5. And it's not the case that factors on one side divide the other. And so if you go further in the subject, you talk about what does it mean to be prime? What does it mean to be irreducible? These are not the same when you leave the integers. So not all properties of the integers continue as we go to these rings. And these rings are very important when you study things in number theory. And so the goal here is to show you that when we are trying to build things from the integers, not every property is going to survive. Also, not every generalization is going to work. So we showed that we can't do something just of the form a plus b pi. We can't do anything of the form a plus bx unless x satisfies a quadratic. Could we come up with a ring that satisfies a cubic? Oh, shoot. I need a blank page. So if x equaled the cube root of 2, then Sx equals a plus b cube root of 2, not a ring. And it field closure, right? But we could look at an extension of this. Instead of a plus b cube root of 2, we could make it a little bit bigger. So what can I do? It'll be all the forms of a plus b cube root of 2. Any thought about what might come next that we could try? So you can view this as a times 1, then b times the cube root of 2. So I got from here to here by multiplying by the cube root of 2. What might you try over here?
multiply by the cube root of 2.
Okay, so what should I try? C times. Can someone help me? What should I put there? I multiplied 1 by the cube root of 2 and I got the cube root of 2. If I multiplied by another cube root of 2, what would I get? I could just write if you want as the cube root of 2 squared, right? And now, if I try to multiply various numbers, remember, whenever you have the cube root of 2 cubed, you get an integer. And so now if you tried, a plus b cube root of 2 plus c cube root of 2, let's do it maybe a1, b1, c1, cube root of 2 squared, times a2 plus b2 cube root of 2 plus c2 cube root of 2 squared, do we think that that's also going to be of the form integer plus integer times cube root of 2 times integer plus cube root of 2? Yeah, I could go through and do all the multiplications. I wouldn't be happy, but I could. But clearly, when a1 hits anything, are we going to be okay? If b1 cube root of 2 hits anything, when it hits a2, that's fine. When it hits b2 cube root of 2, that's fine. And when it hits c2 cube root of 2 squared, that's going to give me a b1 c2 cube root of 2 cubed. And what's the cube root of 2 cubed? 2, which is going to be an integer. And similarly, when the cube root of 2 squared hits the first one, it's fine. When it hits the second one, it's going to give me a 2. When it hits the third one, it's going to give me a cube root of 2 times 2. It's going to be fine. So you can show that this works. So this is a ring. So more generally, exercise. If alpha solves a polynomial of degree n with integer coefficients and no lower degree polynomial, then R alpha equals A1 plus A2 alpha plus A3 alpha squared plus dot 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 plus A n minus 1 alpha n minus 1 each AK in Z is a ring. And the reason is when I multiply two things of this form, if alpha to the n minus 1 is hit by an alpha, that gives me an alpha to the n, which satisfies a polynomial with integer coefficients, I can reduce. So this is a really good exercise for you to do. Go through and show that this is a ring. This gives us some examples. So if I gave you a number like pi, pi does not satisfy a polynomial of finite degree. And because of that, I can't construct a nice ring like this. Okay, any questions about this? Okay, so the next is, we've talked about homomorphisms, we talked about them from groups to groups, we've talked about them a little bit from rings to rings. Our go-to ring should always be either something with the clock or something with the integers. And it turns out that there is a unique homomorphism from the integers to any ring. And part of this goes back to, we require a ring homomorphism to send the identities to the identity. Right? So do you agree that this is forced on us? That we have to send 1 to the identity in R, we have to send 0 to the identity. This is by the definition of a ring homomorphism. So we have no choice. Now let's see if we have a choice for anything else. We know what it sends 0 and 1 to. How would you calculate phi of 2? We know what it sends 0 to, we know what it sends 1 to. Well, how should I calculate phi of 2? I want to somehow exploit properties of a ring homomorphism. So what properties does a ring homomorphism have? What makes something a ring homomorphism? So it's got to be nice with respect to addition. It has to be nice with respect to multiplication. So we need P of A plus B is P of A plus P of B, and P of AB is P of A, P of B. Right? It doesn't matter if I add and then apply phi, or if I apply phi and then I add. Most things in life are not like that. If you have a bank account, does it matter if you deposit the money and then they calculate the interest, or they calculate interest and then you deposit the money? It matters. The order in which you do those operations will result in a different value of your bank account at the end of the day. These homomorphisms, it basically says order doesn't matter. Either combine them in the first ring and then add them in the second, or move them to the second ring and then add. Doesn't matter. So how should I write 2 so I can exploit properties of what I already know? I know phi of 1, I know phi of 0. What's a good way to write 2 so I can use properties of this ring? Excellent. So phi of 2 is phi of 1 plus 1, which is then phi of 1 plus phi of 1, which is 1r plus 1r, which is 2 times r. It's 2 times 1r. How about phi of 3? How should I write that? I'm sorry? 2 plus 1, because we already know what phi of 2 is. So phi of 3 is phi of 2 plus 1 is phi of 2 plus phi of 1 is 2 times the identity plus the identity, which is just going to be 3 times the identity. Technically, what should I do from this point onward? Generalize. And what mathematical process do I use here? Induction. By induction, phi of n is going to be n times the identity. For which n have I shown this? So for which n have I shown this? What do you think? Have I shown this for all n? Yes.
Other positive integers, or is it really general?
So which? You are correct. Yes. If n is a positive integer. So we've only done it for n a positive integer. We have not done it for the negative integers yet. So I need to figure out how do I handle the negative integers. Well, if I could just do -1, I could probably be okay. Because then I can maybe induct in the other direction. So how do you think I can start getting negatives? Have we used all the givens? What have we not used? 5, 0. So how should I write 0? -1. Yep. Is it 1 plus -1? Yep. So it's phi of 1 plus -1. So it's going to be phi of 1 plus phi of -1, and that equals 0. Therefore, phi of -1 equals the additive inverse of phi of 1 in R, or phi of -1 is negative the multiplicative identity, because we know phi of 1 is the multiplicative identity. So now we know phi of -1. Okay. How would we calculate phi of 2? Or phi of -2? We want phi of -2 how should I write this?
E of -1 plus U.
So we could do phi of -1 plus -1 is phi of -1 plus phi of -1 is -1r plus -1r. And that would be -2r. -2 times that. That's one way to do it. We could also do phi of -2 is phi of -1 times 2, right? Which is phi of -1 times phi of 2. And if we do it like that, then this is negative multiplicative identity times 2 times the identity, which is just going to be -2 times identity. And in general, if we do that, once we know phi of n, I can write phi of -n as phi of -1 times n is phi of -1 times phi of n is negative identity times n times the identity is negative n times the identity. There's often more than one way of doing the algebra. But it's important to remember that it's not enough to just do n positive. The whole point is there was no freedom. If I want a ring homomorphism from the integers to R, once I tell you I want a ring homomorphism, this is what I'm thinking of. Because once I say I have a ring homomorphism, I have to send the identities to the identities. And that's enough to uniquely specify. So if I asked you to study the ring homomorphisms from Z to R, it's kind of boring. We need a more interesting ring. What might be a more interesting ring to look at? So what might be more interesting than the integers? But not too much more interesting, just a little bit interesting. What's close to the integers? What's the next set of numbers that's a little bit larger? The rationals. So maybe, so explore phi from the rationals to R. Is there freedom? We know it's going to have to specify a lot. Does it specify everything? That would be a great exam question. Yep. If I give you that you have a ring homomorphism, is that enough to completely specify what's going on now from the rationals, or do I have some freedom? Okay, so the next is the notion of a field. So a field is a commutative ring with the property that every non-zero element of R has a multiplicative inverse. So basically it's saying, look, we know that we're not requiring everything to have a multiplicative inverse because if I give you the zero element is clearly not going to have an inverse except in one situation. There's only one time when the zero element has a inverse. Anybody know what's the one ring where the zero element under addition has a inverse? Anybody know that one ring? It is the simplest ring you can think of. What elements does a ring have to have? So this right now is you have to be a smartass. It's required. There's no other way to get this problem. What elements does a ring have to have?
Has to have a set. Does it have to be a non-empty set?
So you could actually argue as to, does it have to be non-empty? And now, this is where it's good that we can actually go back and a ring is a set with two operations The set is a abelian group. The identity element of this group is denoted 0 or 0R. So the way it's phrased, I think it is implying that there is a additive identity. So my freshman year math book, we were doing vector spaces, and it sometimes causes trouble if the empty set is considered a vector space. You talk about, if I take two vectors in the set, well, there aren't two vectors in the set. There are no vectors in the set. So you can't get a contradiction. And so the book just said, look, just whenever it causes trouble, just ignore it. You know, we trust you to know when it's going to be a problem. The way it's phrased, I think it has to have an identity element under multiplication and under addition. So no, yeah. You have to have, how many elements do you have to have as a minimum? Minimum number of elements you have to have. Nope. You have to have a multiplicative identity, correct? And you have to have an additive identity. How many elements at a minimum do you have to have? It's not 2.
1.
1. Why do you only have to have 1 element at a minimum?
That element would be both the.
Yeah, what if I give you a set where the multiplicative identity is the same as the additive identity? You have to have 1 of each, but they could be the same. Nothing ever says that 1 is not 0. So what if I give you this set that contains just 0? Is this a group under addition? Yeah. Is it a group under multiplication? Amazingly, yes. What's the inverse of 0? What times 0 would be the multiplicative identity? 0. The multiplicative identity leaves everything alone. If your only element is 0, if you multiply it by 0, do you leave it alone? Yes. This is a ring. This is a stupid ring. But it is a ring. Okay? So we often want 0 not to equal 1. Basically, if 0 equals 1, it's going to be question? Okay. So again, this is just you have to be careful about stuff like this. The way the definition works, this counts as a ring. So frequently we might want to add an additional assumption. I only want to look at rings where 0 is not equal to 1. So a field is a commutative ring that every non-zero element has a multiplicative inverse. So if you're not the 0 element, you can be inverted. So the only problem is the 0 element. That's not an unreasonable hope. That as long as I stay away from the 0 element, do you think that's the case? Do you think that we can have a ring where non-zero elements don't have inverses? So what's the example of a ring where non-zero elements might fail to have an inverse? We've done this a few times already. So what's the example of a ring where a non-zero element is non-invertible?
The integers?
I'm sorry?
The integers?
So the integers. So that fails. If we go up to the rationals, that's okay. So again, when in doubt, if I'm asking you a question, in your mind, try it with the integers. There's another thing you could try it with. What's our other go-to? The clock with how many hours? 12. And so, you see numbers like 2 and 3 don't have inverses. So there will definitely be rings that are not fields. So not all rings are fields. The integers, and then Z mod 12Z, for example. All right, so let's do rings that are field. So unfortunately right now, I've given you 2 examples of rings that are not fields. Maybe no ring is a field. Just because I write down some properties doesn't mean that something exists that has those properties. Can anybody give me a ring that is a field where the non-zero elements are invertible? So the integers did not work. So the number 2 did not have an inverse. How can we fix that? How could we extend the integers? Rationals, excellent. And beyond the rationals, what could we do? Yes, the reals. And beyond the reals, what could we do? To do the complex. So those would be examples of rings that are fields. You could ask, what if we go back and look at these things we were doing before? Do you think that those are going to be fields? And if so, is it going to be a field for every x or just some x? And then for the one down here, if I take alpha solves the polynomial of degree n with integer coefficients and nothing of lower degree, do we think that's going to be a field? So those would be great natural test questions. Can you determine if those are? And again, rather than doing something in general, try doing something particular first. Let's say I give you a plus b squared root of negative 5. Is that a field? And so is s square root of negative 5 equals a plus b square root of negative 5, a, b, and z, a field? What do you think? Yes or no? Can you come up with an element that you think might not be invertible? So every non-zero element has to have a multiplicative inverse to be a field. Are there any elements here that you think might have trouble having an inverse? One is I could give you, a plus b square root of negative 5 and try to find a c plus d square root of negative 5 so that this equals 1. That's what I have to do. And one possibility is to show no matter what a and b you give me, I can always find a c and a d. If I can do that, then I win. Or I could choose a specific pair A and B where there's no inverse. It doesn't matter if 99% of the time I can find an inverse. As long as I can find one situation where it doesn't work, I'm done. So you have two ways to go about this. One is if you think it's true, if you think it's a field, then you have to show no matter what A and B you give me, I can find a C and a D. Maybe you can find it constructively and you can give you, here's the formula of how to write C and D in terms of A and B. Or conversely, if it's not a field, then there has to be a choice of A and B where no C and D work. See if you can find that. So we saw earlier when we were trying to show is it closed when we looked at things of the form a plus b pi. It wasn't closed. Just take pi times pi. It doesn't matter all the other times it was closed. We had one time when it wasn't. So can somebody give me a choice of A and B that might be easy to investigate? Make my life easy. So an element that you think might not have an inverse. What would be nice about one of the A's and B's? What would make your life simple? You've done this before earlier today. What should you choose for one of the A or B? 0. So if you choose one of them to be 0, that's going to make your life a lot easier. Do you want A to be 0? Or do you want B to be 0? A. We have b squared of negative 5 times c plus d squared of negative 5 equals 1. So then we're going to get bc squared of negative 5 minus 5bd equals 1. Is this going to be solvable? Is there going to be a choice of B, C, and D that will make this work? Well, actually, let's make life easy for us. Let's take the value of 1 for B. So we'll try A equals 0, B equals 1. So if you want to solve this, what does D have to be? If you want C times the square root of negative 5 minus 5D equals 1, what does D have to equal? What does C have to equal? How many square root of negative 5s do I have on the right-hand side? None. So what does C have to equal? It has to be 0. What does D have to equal? I need negative 5D equals 1. What does D have to be? Negative 1/5. So this is impossible. Alternatively, I could use this to say C times the square root of negative 5 equals 1 plus 5D, or the square root of negative 5 equals 1 plus 5D over C, which is rational, which is false. There's more than one way to attack a lot of these problems. And so if I write it like this, I would get that the square root of negative 5 has to be rational. And that's impossible. So this proves that I can't find a C and a D to invert the square root of negative 5. I would have probably tried to invert 2. Inverting square root of negative 5 is fine. Almost anything you take, you're going to run into trouble. So in a situation like this, what you want to do is you want to try to correct. So were you able to invert the square root of negative 5? No. But how much did you miss by? You needed to get something of the form C plus D squared of negative 5, where C and D were integers. And you got, it works, but they're not both integers. One is an integer and one is a rational. So maybe instead of acquiring A and B to be integers, what if we looked at A and B to be rationals? Oops, oh crap. I hit copy rather than paste. But what if we look at, consider all the things with the form A plus B square root of negative 5, A and B are rational. Is this a field? Before I determine if it's a field, what should I determine first? If it's a ring, right? If it's not a ring, it's not a field. So it is a ring. I'll leave that to you. So now let's say I give you A plus B squared of negative 5, C plus D squared of negative 5. I want that to equal 1. So the question is, are things invertible? As long as they're not 0. Well, if we multiply this out on the left, we get AC plus, I'm sorry, minus 5BD plus BC plus AD square root of negative 5 equals 1. What must be true about BC plus AD? So if I want the expression on the left to equal 1, what must be true about BC plus AD? What does that have to equal? 0. And how about AC minus 5BD? What does that have to equal? 1. So you get AC minus 5BD equals 1, BC plus AD equals 0, but A and B are given, right? They're your given number. Yes? So I'm going to erase the A's, and I'm going to put them in red because we were told what they are. And I'm going to erase the B's because we were told what they are. The whole point of this is sometimes things can look overwhelming and you have to find what's the right way to look at it. When I first looked at it, I was like, oh my God, I have 4 parameters going on, 2 equations, I got to solve this. But how many free variables do we have? We only have 2. A, B are given, and then C and D are free. Does this on the left remind anybody of anything? Does that look like anything you've seen in any class? Yes, say it out loud. Like a matrix, right? So what we have here is a matrix equation. And so I can write this in matrix form as something CD equals 1, 0. And what are my matrix elements going to be? It's just going to be A minus 5B, B, A. How do we solve this matrix equation? How do you find CD? So if I give you AX equals B, X equals I'm sorry? What do you mean by B of A? I'm sorry? Say it again. Oh, yeah. Oh, B over A? I can't do over. Right? We can't do over in linear algebra. What do you have to do instead of over? You're close. That's why I was having trouble, because you can't say over. It's a word I can't hear. I'm sorry? You have to find the inverse. So does the inverse come on the left or the right of B? Is the inverse on the left of B? Is it A inverse B or B A inverse? Right, because we have A X equals B, so we multiply on the left by A inverse, right? You know, those classes you took, there might have been a reason. You know, there might have been a reason this was the prerequisite for this class. Every now and then I might actually use some of the material. Now, if you want the matrix to be invertible, what must be true? How can you tell if a matrix is invertible? So CD equals A minus 5B, BA inverse acting on 1, 0. How do you tell if a matrix is invertible? I'm sorry? Nope. Because I can give you invertible matrices where the diagonals are not zeros. There's a simple test to tell if a matrix is invertible. And again, it's possible that you didn't do this. I do not know what's done. Determinant. How many of you have done eigenvalues? somebody taught at Williams once without teaching eigenvalues. He thought that that was going to be covered in the second course of linear algebra and didn't realize that there wasn't a second course on linear algebra and was needled about this for decades. But you know, how could you do linear algebra without doing eigenvalues? So we need to check the determinant. If the determinant is non-zero, it's invertible. Determinant is going to be a squared minus, no, plus 5b squared, right? Does everybody agree that it's a squared plus 5b squared is the determinant? Yes? Is that zero? What's the only way zero? A equals b equals 0, which gives 0 plus 0 squared root of minus 5 equals 0. So the only time the determinant is not 0, so the only time the determinant is 0 is when I take the 0 element. Any other choice of A and B give me a determinant that's not 0, so it's invertible, so I can solve for C and D. Will C and D have rational entries? Yes. If I take the inverse of a matrix with rational entries, it will have rational entries. So I don't want to do that in red. So the entries are rational. So you should check that. Somewhere deep in your memory, you might have the inverse of a 2x2 matrix. It's 1 over the determinant, and then you flip the diagonals and put in some signs, right? So the inverse is going to be rational. It's going to have rational entries. This will give us rational choices for C and D. So not only am I able to show that every non-zero element has an inverse, I can even tell you how to find it. It's a constructive proof. So if you give me 3 plus 7 square root of minus 5, I'll tell you what's its multiplicative inverse. You should have had some strange question lurking in your mind from earlier in the lecture. So when we were talking about looking at these sets, over here, a plus bx, we tried x to be the square root of n, and we showed everything worked out nicely. And then we needed an n to try. What would be the most natural n to take that's not a square? It would be 2. I didn't do that. I chose 5. No, I didn't. I didn't choose 5. What did I choose? I chose -5. Why would I choose -5? If I'm not going to be 2, if I'm being cute, why not at least do 5 and not -5? Well, now, after we've gone through a lot, because I had that negative sign, I'm getting a plus sign over here, and there's no way that can be 0, because I've got a squared plus 5b squared. And so now we see the dividend of choosing the -5. So my question is, would there be a problem if I had chosen the square root of a positive number? So for which n will this be a field? And can you always find explicit constructions? If I gave you the cube root of 2, instead of a 2x2 matrix, what do you think would happen? What do you think you would have? Instead of a 2x2 matrix, you would have what if I give you the cube root of 2? Probably a 3x3. And then you'd have the joy of a 3x3 inverse to compute. But this is where you say, hey, look, just take the inverse of that. And you would need to make sure that the determinant is not 0. For a 2x2 matrix, it's not that bad for me to write down explicitly and show that the determinant is not 0. How many of you have done some statistics? Not many. Just one. Only one person has done some. So no one, almost no one has seen like the method of least squares, finding best fit lines. All right, maybe 2 now. When you're doing a lot of these processes, if you want to find the best fit line, there's explicit formulas that work, unless you're a complete moron. So you're gathering data and you want to try to find the best fit line. You believe Y equals ax plus b, and trying to find what's the best value of a and b. So maybe you have an inclined plane and you have a ball rolling down on it, and you want to see how does the time to roll down depend on the angle. So what should you do to try to figure out how the time depends on the angle? What should you do? Change the angle. Good. The method of least squares will give you a best fit line as long as you change the angle. If you want to try to figure out how the time to roll down depends on the angle, and you only measure at 30 degrees, do you have any hope of finding how the time depends on the angle if all of your data comes from 30 degrees? No. You end up having a matrix that you need to invert, and the determinant of the matrix is 0 if every point has the same angle. As long as you have some variation, the determinant will have a non-zero value, and it will be invertible, and you'll get best fit parameters. And so in a situation like that, you can actually show that the determinant will be non-zero very easily, because you can interpret the determinant as the standard deviation of the data. And so as long as the data has some variation, it's not zero. But over here, if I were to give you the cube root of 2, and you start to write down your matrix, is it immediately clear? I can roll up my sleeves and do the calculation, okay. But what about a general one? What if I get the fourth root of 2, the fifth root of 2? Will I be able to prove stuff like that always have non-zero determinants? And so there are interesting methods to try to solve problems like that. And so sometimes for small values, you can just brute force it. But those methods don't always generalize as you go higher up. So, again, for a small problem, by all means, do it by brute force, get some intuition, get a feel for what's going on, but be aware that the general case might be a lot harder. So we now at least have a non-trivial example of a field. Excellent. Okay, so let R be a commutative ring. An element A in R is called a zero divisor if A is not 0 and there's some non-zero B such that AB equals 0. So a lot of the restrictions are, we don't want to consider 0 to be a zero divisor. And we want A times something to be 0. Well, if you multiply anything by 0, what do you get? If I multiply anything by 0, what do I get? 0. So we want B to be non-zero. So the ring is an integral domain if it has no zero divisors. Equivalently, the ring is an integral domain if the only way to get AB equals 0 is either A is 0 or B is 0. So can somebody give me an example of something that's not an integral ring? Example of a non-integral ring. So this means it has zero divisors. So I want a ring where two non-zero elements multiply to a zero element. So this is one of our go-tos. So can you give me a ring where two non-zero elements multiply to 0? Good. So if I look at my clock, there's Z mod 12Z. So give me two numbers now. Good. Those are actually the ones I was 3 times 4 is equal to 0 mod 12. More generally, Z mod NZ if N is composite. So those will always be examples of non-integral rings. And the hope maybe Z mod PZ is an integral ring if P is prime. So we know if N is composite, if N is 3 times 4, if N is 8 times 17, those give me obvious candidates that are going to fail. So the hope is as long as we don't have that, we will have an integral ring. Okay, that would be a great exercise. Can you prove that? All right. Cancellation property. So a commutative ring R is said to have the cancellation property if whenever you have AB equals AC, you can just cancel the A's and get B equals C. Or there's one other thing you have to be careful about. Or A was equal to 0. Right? Yeah, 0 times 3 equals 0 times 7. That doesn't mean 3 equals 7. So the only way I can have AB equals AC is either A equals 0 or B equals C. And then the next line is what you would expect. A commutative ring has the cancellation property if and only if it is an integral domain. And so what does if and only if mean? It means it goes both directions. If it's an integral domain, then it has the cancellation property. If it has the cancellation property, then it's an integral domain. And so now you have two directions to prove. So you have to prove cancellation implies integral domain. And you have to prove integral domain implies cancellation. And so you want to try to figure out how do I want to do this? I've got to do a lot of things eventually. Sometimes rather than proving what's given, it's sometimes easy to prove logical equivalence. Somebody remember the, P, if P then Q is the same as like not Q. I'm going to get it wrong unless I write the truth tables. Have you seen stuff like that? Where you flip things around. So sometimes you have to think for something like this, do I want to prove the statement like that, or do I want to look at maybe if it's not an integral domain, does that mean that it doesn't have the cancellation part or something like that? So you have to figure out which is the easier thing to try. If you're not sure, do the advice from Zootopia. Anybody, is this too early for people? What's the big song she sings? Try everything, right? If you're not sure, try everything. There's only a couple of things we can try, right? Let me try proving the original statement. Let me try proving the logical equivalent. Let me try using all the different things I know. And hopefully one of them will work. So think about this for the next class as to how would you prove something like this? Okay, so this is a good place to stop for today. So we are getting to a lot of good ingredients. We're beginning to see generalizations of the integrals. I will end with one fun fact. Can somebody factor sine squared x? Can you write sine squared x as a product of functions? Sine x times sine x. It also equals 1 minus cosine x times 1 plus cosine x. Because if you multiply this out, you would get 1 minus cosine squared x. And since sine squared plus cosine squared is 1, sine squared is 1 minus cosine squared. So you can look at rings involving functions. And now I've got this sine squared. I can write this two different ways. Just as another interesting example of unique factorization. It's a really nice property that the integers have. Not everything is going to have that. All right, so this is a good place to stop.